This is a video walkthrough for the final exam review for pre-calculus. In number 1, we're asked to find f of x minus 4. If f of x is equal to 5 times x plus 3, then f of x minus 4 is equal to 5 times x minus 4 plus 3. Simplify by distributing and combine like terms for 5x minus 17. In number 2, we're asked to find the value of g of x minus 5. G of x is x squared plus 3 times x plus 1. If we replace all those x's with x minus 5, then we get x minus 5 squared plus 3 times x minus 5 plus 1. X minus 5 squared is x squared minus 10x plus 25. And 3 times x minus 5 is 3x minus 15. And now if we combine like terms, we have x squared minus 7x plus 16. Oops, I mean 11. 25 minus 15 is 10 plus 1 is 11. In number 3, we're asked to find f of g of x. If f of x is 5x plus 3, f of g of x is 5 times g of x plus 3. And g of x is x squared plus 3x plus 1. Simplifying 5x squared plus 15x plus 5 plus 3, or 5x squared plus 15x plus 8. In 4 through 6, we're given functions, f of x, g of x, and h of x, and we're asked to find x if f of x is equal to 14. So I'm going to replace f of x with what it is equal to, 3x plus 2, and solve the equation 3x plus 2 is equal to 14. And that gives us an x value of 4. In 5, we're asked to solve the equation g of x is equal to 2. So I'm going to replace g of x with what it is equal to, x minus 3 squared equal to 2. We can solve this equation by taking a square root on both sides. Don't forget plus or minus, there are 2 solutions. And then adding 3 for 2 solutions. 3 plus the square root of 2 is 1, and 3 minus the square root of 2 is the other. In number 6, we're asked to find x if h of x is equal to 2 times the square root of 5. So I'll replace h of x with what h of x equals, and then undo the square root by squaring both sides, and then subtracting 1 to get x equal to 19. In number 7 through 11, we're referring to the graph of y equals f of x at the right. To find f of 4, it's important that we realize that x is being replaced with 4. So f of 4 is what the value of y is. So I'm going to go to 4 on the graph, find that point, and when x is equal to 4, the y value is equal to negative 2. In number 8, we are finding f of 5. And on the graph, when x is equal to 5, there is no y value, so this will be undefined. In number 9, we're asked to find x if f of x is equal to negative 3. This time we have the y value, and we are looking for the x value. So if y is equal to negative 3, we can run a horizontal line at y equals negative 3 and see where it intersects the graph, and it intersects it at x equals 3. In number 10, we're asked to find x if f of x is equal to 0. We can use a similar strategy for this, run a horizontal line with a y value of 0, and notice that it intersects the graph in 3 places. It intersects at x equals negative 3, 0, and 2. Number 11 asks us not for the specific values, but for how many values of x is f of x equal to negative 1. So I'm going to draw a horizontal line at y equals negative 1 and look at the number of intersections there, and there are 3 values there. We don't care what the values are. Number 12 through 15, we're evaluating expressions and simplifying them. If h of x is equal to x squared minus 3x, we're going to need the value of h of negative 1 to simplify. So h of negative 1 is negative 1 squared minus 3 times negative 1. If we do the arithmetic, that number is 4. So that means that this expression is h of x, which is x squared minus 3x, minus h of negative 1, which is negative 4, divided by x plus 1. From this point, the numerator can be factored into x plus 4 times x minus 1, or rather x plus 4 times x plus 1, and then we can simplify, and that's x minus 4 in simplified form. In 13, we have a function g of x is 1 over x, and we're going to need the value of g of 4. G of 4 is 1/4. So g of x divided minus g of 4 over x minus 4 is 1 over x minus 1 over 4 divided by x minus 4. In order to simplify a complex fraction, we need to multiply numerator and denominator by the least common denominator of 4x. I'm going to distribute to each of the terms, and that will give us 4 minus x on the top, and then on the bottom 4x times x minus 4. X minus 4 and 4 minus x are opposite factors, so when we cancel those, that will leave us with a value of negative 1 in the numerator. So this simplifies to negative 1 over 4x. In 14, f of a plus b minus f of a over b can be simplified, but let's just do one part at a time. F of a plus b is a plus b squared plus 2 times a plus b, and f of a is a squared plus 2a. Now we've got to subtract, but when something follows a subtraction, if it has multiple terms, we have to use parentheses or brackets there. And so now if we simplify from here, this is equal to a squared plus 2ab plus b squared. That's the square of a plus b. And then 2 times a plus b is 2a plus 2b. And then distribute the minus sign. That's minus a squared minus 2a. And then that's all over b. What we'll notice is that some of the terms will go away. We have opposite pairs of terms in the numerator, a squared and negative a squared, and also positive 2a and negative 2a. The remaining terms have a common factor of b, so we're going to factor the b out, 2a plus b plus 2, and then divided by b. The factors of b can be canceled, and we get 2a plus b plus 2. In number 15, we have a similar expression. F of a plus b is 1 over a plus b, and f of a is 1 over a. And then that's all over b. We're going to simplify the complex fraction by multiplying by the least common denominator, which is a times a plus b. Now distribute to each of the terms, and that will leave us with a for a first term minus, and the quantity a plus b is left in the second. In the denominator, we have a times b times a plus b, and as tempting as it may be to cancel common factors of a plus b is not really a factor of the numerator since it follows a minus sign. So we're going to simplify a minus b minus, rather a minus b divided by ab times a plus b, and then our numerator simplifies to just negative b, and then we can cancel common factors of b, and that will leave us with negative 1 over a times a plus b. In number 16, we can set up a table of values. X are our input values. We have to do the inner parentheses first. That's 3 minus x, and then take f of that value, and finally for the y value, multiply that value by 2. And so the input and output for the function are those two columns. That's where we're going to put the parent function points, negative 2, 2, 0, 4, 2, 0, and 4, negative 2. In order to work backwards from 3 minus x to x, we have to solve the equation 3 minus x is equal to negative 2, for instance, and subtract 3, and then divide by negative 1, and that'll give us an x value of 5. We can do that similar process for the rest of the values, and we should get 3 and 1 and negative 1. And then to find the last column, we just need to double the values in the third column. So 4, 8, 0, and negative 4. So our ordered pairs are 5, 4, 3, 8, 1, 0, and negative 1, negative 4. In 17, I'm going to set up a similar table of values. Pick the x values, take their absolute values, and then subtract 2, and then take f of that value. Here are the inputs and the outputs for the function. That's where our parent function points are going to go. Negative 2, 2, 0, 4, 2, 0, and 4, negative 2. In order to move from the absolute value of x minus 2 to the absolute value of x, we're going to add 2. So adding 2, and then if the absolute value of x is equal to 0, x must be 0. If the absolute value of x is equal to 2, then x must be either positive or negative 2. Similar for 4 and for 6. So now we actually have many more points to graph than the original function had. So we have the point 0, 2. We also have 2, 4 and negative 2, 4. 4, 0 and negative 4, 0. And finally 6, negative 2 and negative 6, negative 2 connecting. We get an interesting looking graph. For 18, I'm going to set up a table of values. X, 1/2 x, f of 1/2 x, and finally the absolute value of f of 1/2 x minus 3. I'm going to combine those last two operations into one column. The inputs and outputs for the function are right there. That's where we're going to put our parent function points, negative 2, 2, 0, 4, 2, 0, and 4, negative 2. If 1/2 x is equal to negative 2, then x must be negative 4. If 1/2 x is 0, then x is 0. If 1/2 of x is 2, then x is 4. If 1/2 of x is 4, then x is 8. And to get the values on the right, take the absolute values of each of the values in the third column and then subtract 3. The absolute value of 2 is 2, minus 3 is negative 1. The absolute value of 4 is 4, minus 3 is 1. The absolute value of 0 is 0, minus 3 is negative 3. And the absolute value of negative 2 is 2, minus 3 is negative 1. So now we can graph our points, negative 4, negative 1, 0, 1, 4, negative 3, and finally 8, negative 1. And the resulting graph should look like that. In 19, I'm going to set up a table of values, starting with the value of x, and then inside parentheses, add 3, and then f of x plus 3, and finally I'm going to do the last operations outside of f of x all in one, negative 1/2 times the f of x plus 3 minus 5. And so here are our input and output columns for the function. So if the input for the function is negative 2, then the output is 2. If the input is 0, then output is 4. Input is 2, output is 0. And input is 4, output is negative 2. If x plus 3 is negative 2, then x is negative 5. In other words, we're subtracting 3 to get the x values. And then to get the values on the right, we're going to multiply by negative 1/2 and subtract 5. Negative 1/2 times 2 is negative 1, minus 5 is negative 6. Negative 1/2 times 4 is negative 2, minus 5 is negative 7. Negative 1/2 times 0 is 0, minus 5 is negative 5. Negative 1/2 times negative 2 is positive 1, minus 4, 5 is negative 4. And now we're going to graph negative 5, negative 6. And next, negative 3, negative 7, negative 1, negative 5, and finally 1 comma negative 4. And the resulting graph should look like that. In number 20, we can set up a table x, and then we have to multiply by 2 and add 6, and then take f of that value and then subtract 6. So our input and output values are going to be negative 2 comma 2 minus 6, which is equal to negative 4, and 0 comma 4 minus 6, which is negative 2, and 2 comma 0 minus 6, which is negative 6, and finally 4 comma negative 2 minus 6, which is negative 8. If 2x plus 6 is equal to negative 2, solve that equation by subtracting 6 and then dividing by 2, and that will give us negative 4 as an x value. 2x plus 6 equals 0. We can solve by subtracting 6 and divided by 2. That would give us negative 3. If 2x plus 6 is equal to 2, then x is negative 2. If 2x plus 6 is equal to 4, then x is equal to negative 1. Now let's graph those points. Negative 4 comma negative 4. Negative 3 comma negative 2. And now negative 2 comma negative 6. And finally negative 1 comma negative 8. In number 21, columns are x, 1/2 x, and then negative, f of 1/2 x. And then final column, negative 1 times f of 1/2 x plus 5. Input and output for the function go here. If a half x is equal to negative 2, then x is negative 4. Or to get the x values, we'll double the 1/2 x values. And then for the final column, we need to multiply each of the values by negative 1 and then add 5. So negative 2 plus 5 is 3, negative 4 plus 5 is 1, 0 plus 5 is 5, and 2 plus 5 is 7. So negative 4 comma positive 3, 0 comma 1, 4 comma 5, and 8 comma 7. And the resulting graph will look like this. In number 22, we're asked to graph the inverse in the same coordinate grid. So our function has xy pairs of negative 5 comma 3, 0 comma 2, 3 comma 1, and 4 comma 0. So that means that our inverse will have coordinate pairs where x and y are swapped. 3, negative 5, 2 comma 0, 1 comma 3, and 0 comma 4. We can plot those points. 3 comma negative 5, 2 comma 0, and I graphed that wrong, 2 comma 0, 1 comma 3, and 0 comma 4. And there's the graph of the inverse, which I'll label f inverse of x. In 23 through 26, we're asked to find the inverse of each one-to-one function and use function notation in the answer. So the inverse is found by swapping x and y. So if f of x represents y, then when I swap them, I'll get x equals 1/6 y minus 5. I'm going to clear fractions first, and then add 30. And now the function deserves a name, so we're going to name it f inverse. So f inverse is equal to 6x plus 30. In number 24, the inverse is found by swapping x and y. And then we need to solve by adding 5. multiplying by 2, and taking a cube root, and finally adding 3. So that means that our original function was named g, so this function is named g inverse of x equals the cube root of 2x plus 10 plus 3. In 25, I'm going to begin by swapping the y variable, which is h of x, with x, and the x variables with y. I'm going to clear the fraction first by multiplying by y plus 7, distribute, and then solve for y by moving all terms with y to one side of the equation and factoring y. So that means y, which is the inverse function of h inverse of x, is equal to 7x divided by 4 minus x. In 26, I'm going to begin by swapping the y variable with x and the x variable with y. And we can begin solving for y by subtracting 2. And then undoing the cube root with cubing both sides. And finally subtracting 1. And since the original function's name was p of x, b inverse of x is equal to x minus 2 cubed minus 1. In 27 through 30, we have a table of values, and if we're asked to find f of 1, we're asked to find the value of f of x if x is equal to 1, and if x is equal to 1, the y value is 4. If we're asked to find f of 0, we are finding the y value when x is equal to 0. Here's x equals 0, and the y value is 7. If we're finding the value of f inverse, we can create a new table where we swap x and y. So f inverse of 1 is the value of f inverse when x is equal to 1, which is 3. F inverse of 4 is the y value of f inverse when x is equal to 4, which is 1.